Okay, so I've had a number of people who have asked me about the numeracy quiz. If you click on quizzes, you can do this on your mobile device as well. And you scroll down. My numeracy quiz right there. Because so many people were having trouble with it, first of all, at the end of chapter 4, I put it there so you can find it easier. Let me actually move this. Okay. So I will give you some more time to get that done, let's say until next Sunday, because I've got given you some homework assignments as well. Thank you to those of you who searched diligently and were able to find it. There it is for you. All right. Let's see. Turn this off now. So among your assignments, I have posted active chemistry assignments, homeworks 10, 11, and 12. I've spaced them out due Wednesday, Thursday, and Sunday. So number 10 is a little bit of balancing equations and a little bit of translating equations. So if you turn and look at the board on the back where it has written out in words, sulfur dioxide reacts with oxygen to form sulfur trioxide. That's what I mean by translating an equation. Now on active chemistry, they give you the reactants, the starting materials, and you just have to finish it off based on the words. So this is going to use your name to chemical compound skills, and then also recognizing the different ways we can represent that arrow: to form, decomposes to form, reacts to form, yields. All of those things can mean that arrow. And then the key thing to remember with that is that it says it wants a balanced chemical equation. So after you figure out what the products are, then you have to go back and balance it. So you have until Wednesday to do that one. And then Thursday is more about predicting reactions, what we've been doing in class for the last couple of weeks. And then the one on the 12th involves a little bit of predicting a little bit of identifying reaction types, but including solubility rules. I think that's the way it is. Either 11 or 12 involves solubility rules, and the other one's more focused on what type of reaction this is. So one of the two. So I've tried to spread out the due dates on those so they're not all right on top of each other. So you do have a test coming up on Wednesday of next week. I will probably do a quiz. I'm thinking Friday, covering some of the material that we have been going through in chapter 4. So deciding what kind of reaction we're looking at, deciding whether or not something is soluble, that kind of thing. I did want to start with a couple of examples, but before I get to that, does anybody have any questions about stuff coming up, that kind of thing? Okay, so reaction types. We have been talking about a couple of different ways to describe them. Some things that you should know is that different books and manuals and whatnot have different names for things. So what I've been calling synthesis is also called a combination. You're combining things. It's also called addition. So all of those kind of fit into the same category. Synthesis and decomposition may or may not be may or may not be. So redox was the one we introduced at the end last Wednesday. and we'll get into more details on what that is. But these are the two that it's like, they don't fit neatly into a category in our second method of dividing things up, because sometimes we're doing oxidation reduction, sometimes we're just combining things. So they don't fit in nice and neatly. Your double displacement generally are not redox. And there are two kinds of double displacement where we switch partners. So do you remember those two? One of them is an acid base. We're dealing with a neutralization where water is one of our products. One of them is precipitation. And then our single displacement this is always redox. So you may sometimes have choices that includes, is this an oxidation reduction reaction? And you're thinking, it's a single displacement reaction, but single displacement isn't on the list. That's when you choose oxidation reduction reaction. Or conversely, you may think that one's not an oxidation reduction reaction, but I don't see, you know, everything on here looks like it would probably be an oxidation reduction. That's when you think, oh, maybe it's one of these two. Okay. So just some ways to think about dividing those up. All right, so let's think about how we might predict products in a reaction. Two examples here. HNO3 plus BaOH2. So usually before we decide what we think the products are going to be, it's a good idea to decide what kind of reaction it is, because that's going to help us figure out what those products might be. So think about what those might be. I'll put the second reaction up as well. All right, so what kind of reaction do we have going on up here, the top one? What do you think, Chris? It is definitely a double displacement. So we have two kinds of double displacement. Which one?
Acid base.
Acid base. So this has an H out front, which is a strong indicator it's probably an acid. And then this one has the OH, our classic example of a base. So that's probably going to be an acid-base reaction. What's the name of this acid? Nitric acid, because we've got nitrate there. And then this is barium hydroxide. So for double displacement, one of the products of an acid-base neutralization is going to be what? Water. Okay, so we're just going to go ahead and put down water. And then we also have the other ions are going to get together. They're going to form a salt, which is, remember, it's just another way of saying an ionic compound. Okay, so what is going to be that ionic compound? Barium nitrate. Okay, now I've got the ions together. I have to think about charges. What's the charge on a barium? 2, positive 2, because it's in this orange column here. So second column. Nitrate is, so we can look over here. It only has one hydrogen, so that indicates it's a -1. So what do I need to do? Do I need more than one nitrate?
No.
So if I only have one nitrate, I have a -1 and a +2. Do they cancel out?
No.
No, they don't cancel out. So I do need more than one, which means I put parentheses around this. And how many do I need? 2. Okay. Then on your active chemistry, it would say, okay, now balance this. All right. So I'm going to look at here where I have 2 hydroxides and I have 2 nitrates. Now I don't have a hydroxide on this side, so it's kind of hard to balance that. So I'm going to start with the nitrate. So I have 2 over here. So I'm going to put 2 HNO3s. And then I'm going to count. I have 2 hydrogens plus 2 more is 4 hydrogens. And over here I only have 2 hydrogens. And here I have 2 oxygens, but over here I only have 1. So I got to put a 2 here. So now I've got 4 hydrogens, 2 oxygens. I have 1 barium and 1 barium. I have 2 hydrogens and 2 oxygens. And over here I have 2 hydrogens. So my hydrogens check and my oxygens check. And I used my nitrates to balance, and the bariums were okay, so I'm balanced. Okay. All right, what kind of reaction is this one? It is a precipitation, which is a kind of double displacement, okay? So this one's going to be precipitation, which tells us that one of our product is going to be insoluble. So these are dissolved, okay? We're just going to switch which cation is attached to which anion. So one way you can do that is put the inside things together and put the outside things together. So we're going to put a barium with a phosphate and a sodium with a chloride. Okay, now we're most familiar with sodium and chlorine. Is this how these two go together? No. No? What's the charge on sodium? +1, because it's in the first column. What's the charge on chlorine? -1. Is this how these two go together? Yes. Okay, so this one's good. Barium phosphate is going to be a little trickier. We said barium was +2. Phosphate is what? What? Negative, but not -2. It's -3. So that's not one we deal with very often, but it is on our list of things. So we're going to have to do that rule where we swap the numbers. So the reason we're going to do that is if I have 3 bariums, then I'm going to have a +2, a +2, and a +2. That will give me +6. And if I have 2 phosphates, then I'm going to have a -3 and a -3. And that's going to give me -6. Okay, so those are my compounds. Now to balance this. Okay, so I have 3 sodiums here. So I'm going to put a 3 over here. And then I have 2 chlorines over here. And suddenly I've got an even number, an even number over there, an odd number over here. So now I'm going to go back and say, okay, well, what if I double this? What if I make this 6, but then I have to make that a 2. So now I have 6 there. So now let's check chlorine. 6 chlorines. Sodium, we have 6. Chlorine, we have 6. So over here, chlorine, I need a 3 here. So that's going to be 6. And that's going to give me 3 bariums. Well, how many bariums do I have over here? 3. So I'm good on barium. And then I have 2 phosphates. And over here, I have how many phosphates? 2. So that's balanced. That one's kind of a tricky one balancing wise. Okay. So now what I want to do is I want to look at solubility rules. So I gave you one set of solubility rules on Wednesday. And I said there are certain anions and cations that we know are always soluble. So what kind of cations are always soluble? Feel free to look back at your notes from last week. Sodium is always soluble, and I know this because it is where? Group 1. So everything in that red column, including the green hydrogen, those compounds are always soluble. So whatever this is attached to, it's going to be soluble. I don't care what the anion is. I can put any anion I want there. This is going to be aqueous. So probably this is going to be our precipitate. This is going to be our solid. So what we're going to do now is look at what are the rules for deciding things like this. How can I be sure that that is in the soluble? There's one extra one there, so pass it over when you get there. All right. Right, so the first thing on the flow chart there, it says, if yes, go right, if no, go down. So what this means is that in order to follow this flow chart, you're going to need to answer the questions. And if the answer to this question is yes, then I'm going to go this way and find out it's soluble. If the answer to this question is no, I'm going to go down and there's another question. And so that's how you'll find the answer to each of these. Now, before we get to this, I'll show you my fingers here. So you can see I got these brown marks on there. They've actually cleaned up quite a bit. I was working with nitric acid and silver nitrate without gloves on. And this one, you might not be able to tell in the light. It's still very yellow. That's what made me notice that I was not wearing gloves, because this was exceedingly painful. I was like, why does that hurt so much? And I'm like, oh yeah, concentrated nitric acid. So wear your gloves in lab. Okay. So our first question then is the cation always soluble? So what we want to put in that box then is, what are the cations that are always soluble? So we said group 1, but there was something else that fit into that category. Ammonia, okay? Well, group 1 and ammonium, I could write out the name or I could write out the ion that I'm apt to see. Okay, the reason these are always soluble is that they only have a +1 charge. If it were greater than +1, there would be a stronger attraction between the ions and it would be harder to separate them. Okay, so all of our always soluble things are going to be things that are always +1 or -1, because that's going to be easier to separate. Okay, we also talked about what is the rule for the anions that are always soluble. And rather than having like a group we can refer to, we just listed them. So there were 3 I gave you. One of them was nitrate. You remember any of the others? Acetate. So you might like that as C2H3O2, or you can write it out in the semi-structural form, CH3COO. Either way you see that. And then the last one was the very first ion on our list, perchlorate. So ClO4-. Okay, so if we see any of these, and most of the time when we have these precipitation reactions, one of these is gonna be involved. So I would say probably about 80% of the questions you would look at that you have to decide which one is soluble and which one is not. The soluble one will have one of these ions and you'll be like, oh yeah, that's not it. Let me guess the other one. But if for some reason none of these ions appear in here, then you go through the rest of this and decide what the rules are. So on your test next week, what I will do is I will put the bottom half of this chart on here as it is with no additional writing. Okay, so I'm not going to tell you what the usually soluble are, and you have to know what the always soluble ones are. So you need to memorize these and memorize which ones fit into this usually soluble category. Okay, so before we go filling in the rest of this, I want to go to the book and see how the book shows us this. Oxidation reaction. Okay, so it tells us soluble ionic compounds. Okay, so soluble compounds will contain these ions with no exception. So that means it's always soluble. Okay, and then it says these ions with just a couple of exceptions. So these are our usually soluble ones. Okay, so chlorine, bromine, iodine, and fluorine all fit into what category? Which, I heard somebody say something, I just didn't understand what it was. Because group what? Find them on the periodic table, look to the right-hand side. What group is that? 17. Yeah, so group 17 is usually soluble. Okay, now it says anion, so we are looking at things with a negative charge. Outside of the group 1 cations, most of the ones that we look at are going to be in group 2, or they're going to be ones that are usually insoluble. So that leaves most of the transition metals. We're not going to have rules for the transition metals, which means that it depends entirely on whether the anion is soluble or not. So if you see iron, if you see chromium, if you see ruthenium, you're going to say, okay, what really matters here is the anion. If I have something that's usually soluble, like one of the halogens, group 17, it's going to be soluble. If I have something that's usually not soluble, it's going to be insoluble. Okay, for the transition metals. All right, let's see if there's anything else that fits into this. Okay, so these are our ones that are always soluble. So we have acetate. Oh, they have chlorate here, and they have bicarbonate. So we can add those to our list. Okay, so I said perchlorate, but also chlorate, and then hydrogen carbonate or bicarbonate. Those can go up there. Okay, and then the next one for soluble includes sulfate. Now it has a few more exceptions than the halogens does, but it's generally going to be soluble. So down here where it says usually soluble is going to be group 17 and sulfate. All right. So most of the other things, oops, I got to go back here. So I put sulfate in this box, and then I put underneath perchlorate, I put chlorate. So those things are soluble, and I put hydrogen carbonate. Now these look very similar, right? But this is hydrogen carbonate, not hydrogen chlorate, because this is just a C, whereas this one is Cl, okay? So I know when you're in a hurry, you're gonna see that C and you're gonna think carbon. But stop when you think it's carbon and say, wait a minute, is there another letter after that that tells me it's something else? Okay, so this then goes through the exceptions. Okay, so it's generally going to be soluble, but I have to check for the exceptions. So some of these exceptions are silver and lead. Okay, so we saw those as exceptions for both sets of compounds. If I have silver and lead, unless they are combined with something that's just absolutely always soluble, silver and lead are just pretty insoluble. Okay, so if those appear and I'm otherwise not sure, it's probably going to be insoluble. Okay? But if it's not silver and lead, then I have to ask myself, okay, what else is going on? So I'm going to be going back and forth between whether I'm talking about the anion or the cation. So this says anion, which means the negative charge. Okay, so it's the one with a negative charge, a heavy halide. So halide is group 17, right? Heavy means not fluorine. Fluorine's the light. Okay, so is it in group 17, but ignoring fluorine? So if it is in group 17, then in addition to silver and lead being insoluble, so are copper and mercury. If it is not in group 17, or if it's fluorine, then I have to ask myself about the cation. The cation is positive. So I look at the positive thing. So if it wasn't silver, if it wasn't lead, then where is that cation coming from? Might be a transition metal, might be a main group metal, which would mean that it was either the dark blue over on this side or the orange over there. All right, so is the cation in group 2? That's the orange ones. Usually magnesium or calcium, but it could be one of the others. All right, so I'm going to put in here magnesium, calcium, strontium, barium. Beryllium is super, super rare. Can you not see it? There we go. Beryllium is super, super rare, and it just does not behave the way it's supposed to, so we won't deal with beryllium. Okay, so these are the ones we'd be thinking about. Magnesium, calcium, strontium, barium. Those are group 2 ones. Okay, so if I have a sulfate and it is barium sulfate, then I would go, okay, barium sulfate. It is a sulfate. It is not silver or lead, so I go down. The anion is not in group 17, so I go down. It is barium, so then I would say yes to this. That means it's insoluble. Okay. And then if it is not one of these, let's say it's a transition metal, then it would be soluble. Okay. So then our other cases would involve anions that are usually insoluble. So I'm going to switch back to the PC. These things are usually insoluble. Okay. So it's going to include hydroxides and sulfates, which are the two that I have on here, phosphates, chromates, and carbonates. So we could maybe add those in if we wanted to. I don't usually ask about these. But we should include carbonate. So if any of these are my anion, it's probably insoluble because the only exceptions are group 1 and ammonia. And I would have already asked myself about those. But if it is hydroxide, I've got this weird exception with the cation being in group 2. Usually in group 2, it's going to be soluble with this weird exception of, and I forgot to put, I always forget to change this in the computer. The magnesium hydroxide. I keep forgetting that you can't see the camera. Back over here. Okay. So phosphate, chromate, carbonate, generally insoluble. But if I look at something like barium hydroxide, I go over here, is the cation in group 2? If it is, it generally is soluble, with this exception. Magnesium hydroxide is insoluble.
You say you don't usually ask about that?
I do not usually ask about phosphate, chromate. I do sometimes ask about carbon. So I will put this on your test, and I will fill in these, these here. But you need to know what a halide is. You need to know what group 2 is, okay? And I will fix this here as well. Okay, so let's try a couple. Starting with, on the board here, we have, well, let's do the one at the top, barium nitrate. Is that gonna be aqueous or is it gonna turn into a solid? So we start at the top. A little bit more. Okay, is the cation always soluble? So is barium in group 1 or is it ammonium? No, so we're gonna go down. Is the anion always soluble? Barium nitrate, this top one here. Is the anion always soluble? Yeah, because it's nitrate. So in this box here, nitrate is the always soluble one. So since it's yes, that's soluble. Okay. Now the bottom one here, we said that's probably a solid. That's probably our precipitate. So barium phosphate. So again, cation doesn't fit there. Now when we ask, is the anion always soluble? Well, is phosphate in this group? No. So I'm going to go down here. Is the anion phosphate, is that usually soluble? So is it a halogen? No, it's a polyatomic ion. Is it sulfate? No, phosphate and sulfate are different things. So I'm going to go down. Is the anion hydroxide, sulfide, phosphate, chromate, carbonate? Well, it's phosphate. So that's insoluble. Okay. So let's try, put this in a place that doesn't look like I'm trying to say what the answer is. Let's try some of these transition metal ones. So iron chloride, iron 3 chloride, or iron sulfide. Oops, I should just be. Okay, so now we have a transition metal. We don't have rules for most of the transition metals, okay? So we're gonna have to pay attention to the anion, okay? So, is the cation always soluble? Is iron always soluble? Iron always soluble? No. Is the anion always soluble? So in the case of chloride, is it always soluble? Chloride is not always soluble. Chlorate is always soluble. Chloride is not. About sulfide, not always soluble. Okay, so I go down here. And this is where I'm going to divide. So let's look at chloride first. Is the anion usually soluble? So does chloride fit into group 17? Yes. So we're going to go to the right. And remember, we're dealing with iron chloride. So is the cation silver or lead? No. So we're going to go down. Is the anion a heavy halide? So the anion, is it in group 17 and not fluorine? Yeah, chlorine is in group 17, but it's not fluorine. So yes, so we're going to go this way. And then it says, is the cation copper or mercury? We're dealing with iron, so it's not. And this is one place you couldn't really fit in the arrow. So let's stick this in here. The box here that says, if the answer here is no, then this is soluble. All right, now for iron sulfate, we got down to here, and then the question was, is the anion usually soluble? Sorry, iron sulfide, very different. Sulfide, is that one of these two? No, because there's no oxygen there, so it's not sulfate. So I go down all the way to here. So am I dealing with something that's in this box? Yes, sulfide. So that's going to be insoluble. So iron sulfide is what they call fool's gold. So it comes in crystals, which is unusual for gold, but it has the same color as gold. All right, what about, let's do the reaction between, it's a pretty common reaction. This is what I was working with that turned my pH down. Silver nitrate. And we'll react it with hydrochloric acid. Now, since this is not a base, we wouldn't consider this an acid-base reaction. We would just treat this as a precipitation reaction. So we would end up with HNO3, these two getting together, and AgCl. Okay. Okay, so let's just verify that silver nitrate should be soluble in the first place. All right, so acids are always soluble, but what about the silver nitrate? Is the cation always soluble? Silver. Is silver in group 1? No, and it's not ammonium. Is the anion always soluble? Nitrate. Yes, so silver nitrate should be soluble. Okay, then we ended up with HNO3, so that was an acid, and we ended up with AgCl. So if I go down here, my cation is not always soluble. Cl, does that fit into this category? Not always soluble. What about the anion? Cl. Is it usually soluble? Yeah, because it's in group 17. Okay, so I'm going to go to the right for yes. And then I'm going to ask myself, is the cation Ag plus or Pb2 plus? Yeah, Ag is my silver. So that tells me it is insoluble. Okay. Do remember, like I said, most of the time when you have to decide between things, one of the two you're comparing is gonna contain something that is always soluble. So you usually can make a pretty good guess about which one is insoluble. But sometimes you'll just have, is this compound soluble or insoluble? And that's when you kind of have to think through this, okay? I try to leave things on the extreme ends, where if you see silver and lead, it's probably going to be insoluble. If you see nitrates and chlorides and things like that, it's probably going to be soluble. So I try not to use all of these if-then things that fall into these categories down here. Okay. All right. Ooh, time's getting away from me. I want to look at oxidation reduction reactions. So if you want to be sure that you're looking at a oxidation reduction reaction, almost all of them will include a pure element. Now, if there is a pure element at all, it's definitely oxidation reduction. So one example that we have looked at was single displacement. So if you recall, that was where we might have something like aluminum plus copper sulfate, copper 2 sulfate, forming copper and aluminum sulfate. Okay, so pure element here, pure element here. Good indicator for that. The other really common way to do this is combustion. All combustion reactions are going to fit into this oxidation reduction. So usually the way that you know combustion is that oxygen is a reactant. Now, there are things other than organic compounds that can combust, but usually when we ask these as examples, it's going to be some kind of organic compound. So it might be CXHY. So this might be CH4. It might be C2H6. It might be C8HHE, but there's a bunch of carbons and hydrogens. Okay, we talked about combustion analysis. So combustion reactions would be involved in combustion analysis. You add oxygen and your products are CO2 and H2O. Yeah, no, just stretch. Okay. And then if you have a synthesis or decomposition reaction to or from elements, that's going to be oxidation reduction. So for example, we said magnesium plus oxygen forming magnesium oxide. That is a synthesis reaction, but it is also a oxidation reduction because we're starting with elements there. So we said that oxidation reduction reactions involved us determining or involved the electrons moving from one atom to another. So the way we determine how many electrons are moving from one element to another is we have to assign the electrons in the first place. Okay, so each atom in an oxidation reduction reaction, or each atom in the compound, is assigned an oxidation number. Or sometimes we call it an oxidation state. When we are assigning these, we are assuming that any electrons that are in between the two atoms in this bond, rather than being shared like we think of a normal bond, we think of them as belonging to one of the atoms. Okay, so it belongs to the one that is more electronegative. This is a property we'll get into later in the semester, which just means that it has a stronger attraction to electrons. The way we can figure that out is we can say, if it's fluorine, it is the most electronegative. If it is close to fluorine, it is pretty darn electronegative. If it is far from fluorine, it is not electronegative. Okay, so that's kind of our basis. But we have these rules that help us to determine what they are, or what the oxidation number is. So for atoms, pure elements, monoatomic ions, oxidation number is equal to the charge. All right, so for Al, we would say the oxidation number is 0. For Al3+, we would say it is 3+. For oxygen as a gas, it's 0. For oxygen as an ion, oxide, O2-, we would say it's -2. Okay. In compounds, the sum of the oxidation numbers is equal to the charge of the compound. So if I look at NaCl, this is composed of Na+, Cl-. This oxidation number is +1. This oxidation number is -1. I add them together, I get a neutral compound. Okay? So we'll get into more details on all the what ifs on Wednesday. All right. Have a good week.